Have you guys logged into the Zoom? Okay. So today we will continue lecture 9. Oh, actually, we finished lecture 9 last time. So at the very end, we'll talk about some examples of important random variables. So many of these examples are, I think we already learned them in the introductory probability course. So here I will just go over them very briefly. So the first example of the random variable is a uniform random variable, while the density function is basically defined uniformly over an interval. And in order for the density function to be a valid function, so the density should be inverse proportional to the length of this interval. Okay, so that the integration of this density will be 1. So this is uniform distribution. The next is the Gaussian distribution. Gaussian random variable, okay, whose density function is defined by such a Gaussian density function. Okay. And this Gaussian random variable is parameterized by 2 parameters, mu and sigma square. So if we write the density function of fx, it is 1 over square root 2 pi sigma square and e to the power of negative x minus mu square divided by 2 times sigma square. So this is called the mean, or the average value of this random variable. We call it the mean of the random variable. And sigma square is called the variance. We will introduce these 2 concepts later. And sigma is called standard deviation, STD. Okay, standard deviation. And this density function is centered at mu. Okay, that's the mean of this random variable, centered at mu, and it looks like symmetric. So there's a peak around mu, and then the density decreases once we get far away from this mean value. And the speed of this decrease or increase is controlled by the parameter sigma. If we have a very small sigma, if we have a very small sigma, then this density function will be highly concentrated around the mean, meaning that most likely, most of the time, the random variable will take values around the mean value. When the variance is very big, then we have more uncertainty. So this is intuitively how this mu and sigma controls the distribution of this density function. And for the Gaussian random variable, we always, in many cases, we always consider its normalized version. So if we have a general Gaussian random variable, we can define a transformation of this Gaussian random variable by subtracting the mu and divided by the standard deviation, sigma. So this is x is a Gaussian random variable. It follows distribution mu and sigma square. So this can be viewed as a transformation, is a function applied to the random variable x. Okay. And then we can look at the CDF function of this x tilde. Okay, so we follow this derivation. We can show that by doing so, we can prove this after this transformation, x tilde follows a normalized Gaussian distribution. Okay, well, we have zero mean and unit variance. This is the most standard Gaussian random variable. So let's look at let's try to derive the CDF of x tilde. So we follow the definition of the CDF. It means the probability of x tilde less than equal to the value x. But x tilde is defined in this way. So we plug it in. So we have x minus mu divided by sigma less than equal to x. So now we are looking at this event, and this event is related to the random variable x. Okay. And then after some rearrange this inequality, we can solve for this x. So it is equivalent to the probability that the random variable x is less than mu plus sigma times the value small x. Now this is a standard form of the CDF of the random variable x. Right? It's probability of random variable x less than equal to something. So since we know the CDF of x is given as follows, right? This is the so the random variable x follows mu sigma, a Gaussian distribution with mu and sigma. So we simply integrate the PDF of the random variable x from -infinity to this upper limit, mu plus sigma times small x. Okay, and then we are given the PDF of the random variable x. So we plug it into plug in the PDF into this integration formula. We end up with this complicated integration. Okay, so if you look at this integration, we are integrating over z. Z is the variable. Well, this mu plus sigma x, this is a constant, has nothing to do with z, right? So when we plug in the Gaussian PDF formula, we end up with this integration. But remember, we are looking at the CDF of x tilde evaluated at x. Okay. So this small x is the variable. It is right here. So we want to look at so this is the CDF of x tilde, which cannot be evaluated analytically, but we can look at its PDF. So its PDF is the derivative of the CDF, but the CDF is defined through such an integration. So in calculus, we know how to take derivatives of integration. Okay. So using the calculus rule, I think, so here the variable is in the upper limit. So in calculus, we have one formula for computing the derivative with regard to the variable in the upper limit. If you apply that formula, it equals to this one, is sigma times the PDF here with z replaced by x, or with z replaced by mu plus sigma x. And simplifying this formula, you end up with such a Gaussian-like PDF function. So we can show that by doing so, the PDF of x tilde equals to this one, okay? Which we can compare this one with the general PDF of Gaussian random variable. And we can see that it corresponds to the case where sigma equals to 1 and mu equals to 0. So this is basically a zero mean and unit variance Gaussian random variable. Okay. So this is called a normalization of Gaussian random variable. We can subtract the mean divided by the standard deviation. And in many cases, where we will leverage this normalized Gaussian random variable to calculate the probability. And in particular, for this standard Gaussian random variable, we will refer to its CDF function as a phi function, phi x. And based on the definition of CDF, this is basically integrating the PDF from -infinity up to x, the limit x. So if this, so the CDF function, the PDF function looks like something that's centered at 0 and has a unit variance. So this is the PDF function of normalized Gaussian random variable. And the phi function is basically, we want to look at phi x. So phi x is basically integrating this fx from -infinity up to x. Okay, so the x is in the upper limit. So which basically means that we are integrating this PDF function up to x. So this would be the area in the shadowed region will be our phi x CDF. So for such a normalized Gaussian random variable, we can define this. We can look at this standard CDF function. And then we can do the following to calculate the CDF of an arbitrary Gaussian random variable. So let's say we have a Gaussian random variable that is not normalized. It has a mean mu with variance sigma square. So this is not normalized. And then we can first consider its normalized version. We subtract the mean divided by sigma. And we have shown that this random variable follows a standard zero mean unit variance Gaussian distribution. Now we want to look at the CDF function of this unnormalized Gaussian random variable, fx evaluated at x. By definition, it equals to the probability that the random variable x is less than or equal to x. And then we can equivalently rewrite this inequality into a normalized form. Okay, we can subtract the mean divided by sigma on both sides. So on the left-hand side, we have the random variable x, subtract mean divided by sigma. So this is the random variable that follows a standard Gaussian distribution. So on the left-hand side, we now have a normalized Gaussian random variable. On the right-hand side, the threshold value x, small x, is now becomes x minus mu divided by sigma. So this is another value, scalar value. So now we are looking at the probability that such a normalized Gaussian random variable less than equal to this value. And this is essentially the definition of CDF of the normalized Gaussian random variable. So this probability is basically the CDF of phi evaluated at this normalized threshold. And well, this phi x is defined to be the CDF of this normalized Gaussian random variable. So if we know, this shows that if we know the CDF of this normalized Gaussian, then we can leverage this CDF to calculate the CDF of arbitrary Gaussian random variables. So there's a connection between these two. Okay, I think this is lecture 9, and let's continue to lecture 10. Let me pull it out here. So we can consider this, let's consider this example. We have a portfolio that has a return whose return follows a Gaussian distribution. Okay. And this return, so that this return is a random variable. Okay. And we modeled this return using the Gaussian distribution. So the return R is a Gaussian distribution centered at 50,000 with variance with standard deviation 50,000. So it looks like this. It is centered at 50,000 with a very large variance. So that means in expectation or on average, we are expected to get a return of 50,000. But because we have a very large variance, so it is likely that the return may be negative sometimes. Okay, now given this return, given this model of this return, we need to look at the value at risk. This is a quantity defined as the follows. So the value at risk called VAR is defined to be the maximum amount that this portfolio can lose with probability 5%. So according to this sentence, so we are looking at this event. So this is an event, the maximum amount that the portfolio can lose. We are looking at this case where this event happens with probability 5%. And because the return follows such a Gaussian distribution, right? It is centered at 50K with such a large variance. So so let's call the maximum amount as V. So we are looking at, so the maximum amount that the portfolio can lose, suppose it is V, we are looking for this V. And then this probability 5% must be equal to, so this, to calculate this probability, we basically integrate this return, the PDF of this return up to this maximum amount, which corresponds to this shadowed area. This area corresponds to the probability that we get a return up to V. So in this shadowed area, we are looking at the event where the return, the amount of return is less than or equal to V. Okay, this is the probability of the event that the amount of the return is less than or equal to V. Okay. Such a probability needs to be 5%. So we are looking for that threshold value V such that the entire probability in this shadowed area equals to 5%. So this is the case where, like, given a if we have a good understanding or estimate of the distribution of the return, we are trying to understand, given a threshold V, we are trying to understand what is the probability that the return is less than or equal to V. Okay, so this is gives us a kind of one perspective to understand the risk when we do the investment. So basically here we are looking at this 5% probability event. So we list out this integration formula, 5% equals to integrating the PDF up to V. So we are looking for a V such that this equation holds. Now, the left-hand side is clear. It is given as 5%, but the right-hand side is standard CDF function. So this is basically the CDF of this random variable R evaluated at V, because we are integrating this PDF up to V. So this is a CDF of R evaluated at V. But we know that this R is a unnormalized Gaussian random variable. We are given this information. So this CDF, the CDF of such an unnormalized Gaussian random variable, we can rewrite it in terms of the CDF of the normalized Gaussian random variable, right? Like we just derived in the previous slide. So by leveraging that equation, this CDF it is equivalent to the CDF of a normalized Gaussian evaluated at V minus subtracts the mean divided by the sigma. Well, here the sigma is 50K also. So this is 50K square. This equals to sigma square. So sigma is 50K. And now this equation now becomes such a standard equation. Well, phi is a standard, it's the CDF of a normalized Gaussian. And there's a table for such a normalized, for the CDF function of the normalized Gaussian. You can check that table and see at which value can we achieve 5% probability. And with that value, you can solve for this V. Okay. If you check the table, in the end, you can get that this V is about negative 32,000. Okay. And put everything together, what we can say is that with more than 95% of confidence, we will not lose more than 32,000 under this portfolio. But because this event happens with probability 5%, so the complementary event happens with probability 95%. So with this much of probability, the return file will be bigger than or equal to this threshold V. Okay, so this is the Gaussian random variable. The other random variable that is very popular is the exponential random variable, and we have seen it in the homeworks. So the PDF of exponential is given as follows. This random variable takes only non-negative values. So in the past, when x is bigger than or equal to 0, the PDF is given by an exponential function with a parameter, with a scaling parameter, lambda. This lambda can be any positive number. So if you look at this exponential PDF, it means that this function decays to 0 exponentially fast. So most likely, the realizations of this random variable will concentrate around 0, or take a very small value because it has a very small tail. And because it decays exponentially fast, so we call this kind of PDF a light-tailed PDF, which means the tail decays very fast. So most likely the random variable will take small values. Now the CDF function can be derived analytically by integrating this PDF up to x. Now if you do a calculus, you can derive the CDF function. It is 1 minus e to the power of negative lambda x, but x is bigger than or equal to 0. Okay, so this is the CDF function. And we have done this in one of the homework problems where we model the bus waiting time as the random variable that follows exponential distribution. And then we are looking at this conditional event. So given that we have already waited for s minutes, what is the probability that the waiting time will be t plus s, which means given that we have already waited for s minutes, what is the probability that we need to wait for an additional t minutes? More than t minutes, actually. So for this event, we are essentially looking at this conditional probability. And by definition of conditional probability, we have this ratio. Well, in the numerator, it's a joint event. But looking at this joint event, this one is strictly contained in this event. So by taking the intersection, we only have this smaller event. While the denominator is the probability of the conditional event. And then these are standard CDF functions evaluated at different values for this random variable. They are not standard. The complementary event is the standard CDF. So we use 1 minus this probability to translate them into the complementary event. Right? So P x greater than s is 1 minus Px less than or equal to s. And this is the CDF function. So that's why here we have 1 minus the CDF. Now the CDF is given as this one for the exponential random variable. So we plug them into this ratio. And after some calculations, we end up with this answer. And this is a very interesting result because we call this the memoryless phenomenon. Well, this conditional distribution does not depend on S. It does not depend on how long you have already waited. So it's like, it looks like the history, it does not depend on history. Your future waiting time does not depend on the history. So that's why we call it memoryless. And we also have this Cauchy distribution. So it looks similar to the Gaussian distribution, but it decays much slower because it's a polynomial. But the Gaussian decays exponentially fast. So for this Cauchy distribution, it has a parameter mu, which corresponds to the mean. Well, the alpha, I think it controls the kind of the variance of this distribution. And this distribution, we call it heavy-tailed because the tail decays polynomially fast. So the tail decays at the rate 1/x². This is a much slower decay compared to the exponential decay. Right? In this exponential PDF, the random variable decays exponentially fast. But here, the random variable, the value, the PDF value, the PDF function decays polynomially fast. This is a much slower decay in general. So we call it, so which means the tail will be much heavier compared to the exponential distribution. So we call this heavy-tailed random variable. Okay. And we have this, so these are the continuous random variables, examples of continuous random variables. And before, we have also talked about many discrete random variables, like Bernoulli and binomial. So I will not go over this. You can refer to the lecture notes. So Bernoulli basically corresponds to flipping a biased coin for once, right? While the probability of getting a head is P, and probability of getting a tail is Q, 1 minus P. Well, binomial distribution corresponds to flipping the coin n times, and we are looking at the probability of observing K heads. So this is binomial distribution. And in fact, this binomial distribution can be represented as can be decomposed into a sum of Bernoulli distributions. So let yi be a Bernoulli P. So this yi corresponds to the observation for the i's flip of the coin. And then the binomial random variable. So binomial random variable is essentially the summation of this yi. Because each yi in each experiment, in each trial, yi may take either head or tail, take either 0 or 1, right? This is a Bernoulli random variable. So these yi are binary random variables. When we sum them up, the summation will equal to the number of ones that we observe in these n experiments, which is exactly the number of heads that we observe. Okay. So this x binomial, this binomial random variable can be decomposed into a sum of Bernoulli random variables. This is a very useful relation that we can leverage to simplify the analysis of binomial distributions. Later, we will leverage this relation to analyze some examples. So this binomial is derived from this Bernoulli by summing them up. And all these yi's are independent. And we also talk about this geometric distribution where we flip a coin n times, and this x equals to k corresponds to the event where we observe the first head until we flip the coin k times. So this means in the first k minus 1 experiments, we always observe tail. And in the last experiment, we observe this head. Okay? So this gives the geometric distribution. Well, basically the distribution follows a geometrically decay function. So I will not go over these examples. So one last thing for the discrete random variable that I want to mention is the Poisson distribution. This is a very important distribution in many that are applied in many applications. Like when we count the photons, the number of photons in an optical system, we always model the number of photons using this Poisson random variable. So this random variable takes such a distribution. The probability of x equal to k is given as follows. Well, lambda is a parameter. E to the negative lambda multiplied by lambda to the power of k divided by k factorial. And if you sketch this discrete random variable, the PDF of this discrete random variable, it looks like an increasing function up to some point and then decrease. And we will see that this lambda controls both the mean and the variance of this random variable. Later, we will show that the binomial distribution, binomial n lambda over n, which means we are running n independent experiments. And in each experiment, we have lambda over n probability to observe a head. Now, such a binomial distribution as n goes to infinity converges to the Poisson distribution. Okay. So all these distributions, they have very strong relation in the limit. And then the last example is a uniform discrete random variable. Well, the PDF, well, the probability mass function is a constant over an interval. Okay. So these are all the frequently used continuous and discrete random variables. Okay. And then in the next section, we are going to talk about a very useful technique called binary hypothesis testing. This is a very important technique if you take any courses in communication, either digital or wireless communication. The setup for this binary hypothesis testing is that we are interested in, so imagine we have a communication channel. We have done this before. Well, the transmitter, somebody wants to send a message. The transmitter wants to send a message to the receiver side to make a communication. And the message may be encoded by binary numbers. Okay. So let's assume this transmitter will send only 0 and 1s. And this message will be encoded by an electromagnetic wave, and that wave will be sent over the air. And we call this the channel. And then after the signal transmitting through this channel, on the receiver side, the receiver will receive a signal, another electromagnetic signal, and try to decode the message based on the received signal. And of course, we always assume that the received signal is the original signal plus some noise. Okay. This is the simplest assumption. And the noise is injected by the channel. And then based on this noisy observation, we want to develop a systematic rule to decode the original message. So basically, in this case, based on the observation on the receiver side, we will need to make a decision on the transmitter side to decide which message does the transmitter send. So in this case, the message of the transmitter is called the hypothesis. We have two possible hypotheses in this that are sent by the transmitter. And based on the observation, we need to do a hypothesis testing and decide which hypothesis should we take. Okay. So let H be a set of hypotheses from which we must select one based on our observations. Right? So in this case, this binary message, these two messages are the set of hypotheses that we can have. And then once the receiver observes receive a signal on the receiver side, he or she must select one hypothesis and to decide. Okay, there are two possible hypotheses, and we must decide one based on the observation. And these are some practical examples. Well, this could be happen to a radar. This can be used to model a radar system. Well, the hypothesis is either there is an aircraft or there is no aircraft. Right? It's a binary hypothesis. And the observation is the received radar signal. Okay. Basically, based on the received, so the radar will transmit the signal over the air, and then it will receive some signal reflected by some objects. Based on the received signal, we need to decide between these two hypotheses, which one is true, which one is false. So there are two different hypotheses. Or in the disease test, the hypothesis could be either a person could be either sick or healthy. Again, a binary hypothesis. And the observation is amount of, based on some statistics, like if the patient does a blood test, then we will have some statistics in the report. And based on those numbers, we will need to decide which hypothesis to take. And there are many other examples, like in face recognition or the communication channel that we just described. And there are many ways to develop such a hypothesis testing framework. And it turns out that the most widely accepted framework is based on probability. So we model everything with random variables, and we perform hypothesis testing using probabilities. So this is what we are going to develop here. So the goal is that once we observe an outcome Y of a random variable, well, what is the random variable? It could be in the radar problem, it could be the received signal. Right? This signal is a random because it may be affected by the random noise injected by the atmosphere. Right? So once we see, if we model the radar signal as a random variable, once we see an outcome or a realization of the radar signal, we want to, based on this outcome, we want to make a hypothesis. So we want to choose, this H hat of Y is a decision rule based on the observation. Based on this observation, this decision rule will help us to pick a hypothesis from the hypothesis set. And such a, we want, in particular, we want that such a decision rule can help us minimize the probability of decision error. Right, this is a very, very intuitive goal. We want to build a decision rule based on the observation that minimizes the probability of decision error. So these are the basic setup of binary hypothesis testing. But we assume we have two different hypotheses, two possible hypotheses. And of course, you can extend this to arbitrary number of hypotheses. But in many cases, or the basic case, is the binary case. And then let's assume that, okay, so in this course, we will take this assumption. This assumption assumes that each hypothesis will occur with a probability, with a certain prior probability. So we are given that probability of hypothesis 0 and the probability of hypothesis 1. For example, if we are looking at this disease test, right? We want to test whether a person is sick or healthy, right? There are two hypotheses, sick or healthy. And as we are assuming that we know for this disease, we already know some prior information. For example, we can collect the information over a large group of people and trying to estimate what is the probability of this disease. For example, in the Utah state, for the Utah people, how many people will get this disease and how many people are healthy. So this gives a prior estimate of this disease. Okay. So we assume that we already know this prior information. So we know on average how often do these two hypotheses occur. And then we also assume that we can compute the following conditional PDF. So this conditional PDF is that given each hypothesis, we can compute the PDF of this random variable y. So this is a conditional PDF. But think about this. Given in the radar example, right? In the radar example, condition on if there is so in the radar example, we have two hypotheses. Either there's an aircraft or there's no aircraft, right? Now, condition on each of these two events, the received radar signal may have a completely different distribution. Right? If there's no aircraft, condition on the event where there's no aircraft, then the received radar signal may be very normal, looks very normal. Right? There's no obstacles in the air. But if there is an aircraft, then the reflected signal may have a totally different distribution. So this is the basis for us to develop a decision rule. Okay. And one of the widely accepted decision rule is the MAP rule, the maximum a posteriori decision rule. We call it MAP rule. So we look at the a posteriori probability, and then we are trying to maximize such a probability to help us make a decision. Okay. So this decision rule is also very intuitive. Now let's look at this decision rule. The decision rule is defined as the follows. Once we observe a signal, y, okay, and this is how we decide under the MAP rule. Now, this is our notation. This MAP rule is a function we denoted as H hat MAP, right? This is a notation. This function will map this observation Y to this binary hypothesis. And the way that it chooses between these two hypotheses is depending on this posterior probability. So basically, it computes these two posterior probability. One is conditioned on the observation, and we condition on your observation, we calculate the probability of that H1 happens under this observation. And we also calculate the probability that H0 happens under this observation. And we just look at these two probabilities and see which one is bigger. And if this one is bigger, if condition on this observation, H1 is more likely to happen, then we simply decide H1. Okay. Otherwise, if this is less than the other side, we choose H0 to be the decision rule. Okay. So this is a very intuitive decision rule. So we simply compute the conditional probability. Condition on your observation, we look at the probability of these two hypotheses. Whichever gives the higher probability will be our final decision. So in particular, we call this the posterior probability because Y is your observation. So we are trying to infer from the observation, we are trying to infer the probability of these two hypotheses. So this such a type of conditional probability is called posterior probability. And according to the conditional probability rule, right, this posterior probability is given as follows. Okay, this is from the previous lectures. It is basically, so in the denominator, we are looking at the probability of the conditional event. But in this case, this Y could be a continuous random variable. So we use PDF instead of the probability. But in the numerator, we use originally it should be the joint event, but then we use the conditional, we expand the joint probability of joint event using the conditional rule. So you can see that this posterior probability on the left-hand side, we are conditioning on Y and trying to infer H, the hypothesis. But usually this is not directly computable. But on the right-hand side, we transform this conditional probability to another type of conditional probability. Well, in the numerator, we only need to look at, given a certain hypothesis, we need to look at the distribution of the outcome. And this is usually can be computed in practice. For example, given there is an aircraft, we usually know the distribution of the received radar signal. So this distribution is usually given. That's why in this setup, we assume that we can have access to such a conditional PDF. Okay. So basically, following this, in order to use the MAP decision rule, we need to compute these two posterior probabilities. And to compute them, we need the following information. We need to know the prior probability of these two hypotheses. And we assume we know that. We need to know such a conditional PDF. And in many cases, we will see many examples, we can compute them. And also we need to know the PDF of this random variable. And again, we can also compute it. Now, if we plug in such a formula, plug this formula into this MAP rule. Okay. So one is conditional on H1, one is looking at H1, one is looking at H0. And then this MAP rule will be simplified to the following rule. Well, the denominator is canceled out because they are common to
to both terms. So in the end, we just need to compare these two products. Okay, so this is the MAP rule. And then equivalently, we can rearrange this decision rule, and then we can translate it into a likelihood ratio test. So equivalently, we just need to rearrange this inequality into the following form, while we put all the conditional PDFs on one side and put all the prior distributions on the other side. Okay. So this will give us the very popular so-called likelihood ratio test. Well, on the left-hand side, we are looking at the likelihood ratio. So this is called the likelihood ratio. Why? First of all, it is a ratio between two terms, right? And second of all, each term is called a likelihood because we are looking at given under different hypotheses, how likely can we observe such a outcome Y? Right. For example, if there is an aircraft, how likely can we observe such a signal? If there's no aircraft, how likely can we observe such a signal? Right? So this is called the likelihood. And when we take the ratio between these two likelihoods, we call it the likelihood ratio. Now, on the right-hand side, it is the ratio between two prior probabilities. And this is a statistics that is usually given or can be estimated from the past based on our past history data or past experience. So on the right-hand side, it has nothing to do with your received signal. Right? So it is more like a threshold. So basically, the MAP decision rule in the end is equivalent to a likelihood ratio test. Well, the threshold for this test is given by some prior information on your hypothesis. And then what you need to do is to compute this likelihood ratio. And then based on the ratio, depending on the ratio and this threshold, you will decide either you pick H1 as the hypothesis or you pick H0 as the hypothesis. And in particular, in some cases, we assume that these two prior information, the prior probability of these two hypotheses, they are equally likely to happen. In that case, this is simply one, and then this MAP decision rule can be further simplified to such a decision rule. We just need to compare these two likelihoods. Okay, whichever hypothesis can we have a higher likelihood, then we will accept that hypothesis. And for this particular case, we call it the maximum likelihood decision rule. So in this case, we only look at the likelihood because the prior probabilities is the same. So we only need to look at the likelihood. So whichever gives the maximum likelihood, we will accept that hypothesis. And this is the case when Y is continuous, but when Y is discrete, it's almost the same. We just need to replace all the PDFs Fy by the probability mass functions. Yeah, everything else is the same. So I think we can take a look at some examples. And I will not go over this, but on lecture 11, we have a derivation to show that the MAP rule, okay, this decision rule which is very intuitive, right? We just compare their posterior probabilities. This decision rule actually minimizes the probability of error over all possible decision rules. This is a very strong statement. Among all the possible decision rules, this one minimizes the probability of error. So that's why it is widely used in many communication and radar systems. And this is the justification, which I will not go over it. We don't have that time, but if you are interested, take a look at these derivations one line by line. Every line in all these derivations, we simply leverage the basic concepts of probability. Okay, I think we can take a look at one example. We have an experiment where we care about this random variable y. This is the observation y. Okay. What is y? Y is the amount of bacteria in a person's blood. Okay. Well, this random variable y is modeled as follows. We model it as exponential distribution with parameter lambda h and lambda s for the healthy and sick persons. Okay, think about that. So y is the number of bacteria in a person's blood. And what we are given is that y equals to exp lambda h for healthy person. And it is exponential. It follows an exponential of lambda s for sick person. Well, we are given that lambda h is far bigger than lambda s. In that case, this is an illustration, comparison of these two distributions. For healthy person, because the lambda is far bigger, so this distribution is highly concentrated. So the tail is even smaller. Okay. For the sick person, the distribution is flattened. It's much wider. Okay. So intuitively, for healthy person, most likely the number of bacteria will be concentrated in the, will take low values. Okay. Will be concentrated around 0. But for the sick person, there's a much higher probability to have more numbers of bacteria. Right. So this is a very reasonable model of this random variable. Okay. So condition on if a person is sick or healthy, we are already given the model of this random variable. And let's assume that the probability that a person gets sick is PS. And this can be estimated by collecting some information from a large group of people. Just count how many sick people are there within, for example, 1 million people. And then we can get this prior information. So let's assume we know this prior information. Given this, find the decision that minimizes the error probability of the disease test. So in the disease test, we observe a person comes to the hospital, right, and did a blood test. We observe the amount of bacteria in that person's blood. Based on this number, we need to decide if the person is healthy or sick. So that is the binary hypothesis testing. So here, this is exactly the setup that we talk about in this MAP rule, right? We have two hypotheses, and we know the prior information, and we are given the model of this random variable conditioned on each hypothesis. So everything's standard. So we just applied the maximum a posteriori decision rule, MAP rule, or the likelihood ratio test. Okay, we just apply this likelihood ratio test. Now let's do that. The likelihood ratio test on the left-hand side is a likelihood ratio. Okay. So here you have to set up everything clearly, right? You define H1 to be sick and H0 to be healthy. So these are the binary hypotheses. And then the likelihood ratio test is the ratio between these two likelihoods. Right? It's a PDF of the random variable Y conditioned on each hypothesis, sick or healthy. Okay. So these are conditional PDFs. On the right-hand side, we are looking at you go back to likelihood ratio. We are looking at the ratio of the prior probabilities of these two hypotheses. So we are given probability of sick to be PS. So the probability of healthy is 1 minus PS. So this is the right-hand side. Okay, and then you just, the decision rule is that if the left-hand side is bigger, then you claim sick. You accept H1. Otherwise, you accept healthy. Right? And in particular, for both of these conditional PDFs, they are given in the problem statement. Okay. So if a person is sick, then the distribution of Y follows such a sick exponential distribution with parameter lambda s, right? Otherwise, if a person is healthy, then the distribution follows such a healthy exponential distribution with parameter lambda h. So you plug them in to this ratio, and we know this threshold. Okay, everything is clear. And because there's an exponential and the ratio involved in this inequality, so a natural idea is to take logarithm on both sides to simplify the expressions. So you take log on both sides, rearrange the terms, eventually you can get this inequality. Because in the end, we want to simplify the decision rule to be on Y only, right? So in this formula, Y is involved in the exponentials, very complicated. We take logarithm, and so that Y can be separated from the other terms. So in the end, okay, we can solve for Y. And this is the decision rule that we are looking at. On the left-hand side, we are looking at the blood test result, Y, a number of bacteria that we have in the blood. On the right-hand side, it is a threshold, and this threshold depends on how you model healthy and sick people and your understanding of the prior information of this disease. Okay. So once you have all this information, on the right-hand side is a number, right? A number tau. This is called the threshold or the decision threshold. So in the end, we want to obtain such a test. Right? This decision rule only looks at your blood test results, and based on this threshold, we can claim if you are healthy or sick. Right? So this is a standard application of the binary, standard application of the likelihood test in the binary hypothesis testing. And you can, with this example, you can work on all the other examples that we talked about before, like if you are looking at radar systems or communication systems, right? You just need to replace the context by the corresponding context in those applications. But the entire setup is exactly the same. And we have 7 minutes. I can briefly talk about two types of errors that we care about, right? So in the end, once you apply this likelihood test or MAP rule, you end up with a decision rule. Okay? This is a hard decision. In the end, based on this decision rule, you make hard decisions. Okay. Now, and inevitably, sometimes you will make errors, right? For example, it is likely that a healthy person somehow has a lot of bacteria in the blood, or a sick person somehow does not have much bacteria in the blood. These rare events can happen, and under these events, your decision rule will be wrong. So you will have some probability of errors. Okay. So in the end, we want to understand, once we derive this decision rule, we want to understand the probability of decision errors. And there are two types of errors that we care about. One is called false positive or false alarm, which means that H0 happens, but you decide H1. Okay. For example, if person is healthy, but you decide is sick, this is a false positive, right? Or there's no aircraft, but you decide there is an aircraft. This is a false alarm, okay? Which means something unimportant happens, something normal happens, but based on your decision rule, somehow you decide the other way. So this is called false alarm. And the other types of errors is the opposite. Well, something important happens, but you missed that. Okay. If somebody is sick, somehow you decide healthy. If there is an aircraft, somehow you decide there's no aircraft. So we call this misdetection. In different applications, we care about different types of errors, right? For example, for a radar system, we don't maybe comparing these two types of errors, we care more about misdetection. We want to minimize this one. Okay, so depending on the application, these two types of errors are treated differently. Okay. Some applications care more about one of these two types of errors. And this is how we calculate the probability of error. Okay. Let's go over these steps. If we want to calculate the probability of misdetection, this event, misdetection, okay, based on your definition, is that following the previous blood example, right? Misdetection means somebody conditioned on someone is sick. Your decision rule outputs healthy. This is called misdetection. Someone is sick, but you claim healthy. This conditional probability is a misdetection error. Now, in particular, more specifically, this means that someone is sick, but your decision rule, okay, in order to claim healthy, based on your decision rule, you must have Y less than your threshold tau, right? This is when you claim healthy. Therefore, this one is equivalent to say that, okay, in your decision rule, So the random variable y takes value smaller than tau. Right. So this is the case when somebody is sick, but somehow his blood has very few bacteria. And then you know this conditional CDF. Well, we are given this conditional CDF. Conditional on someone is sick, the distribution of the bacteria is given by this exponential distribution with the parameter lambda s. So you can compute this compute this probability by integrating the PDF function. Okay. And in the end, you can get this probability of error. And again, for probability of false alarm, that means someone is healthy, but you claim sick, which means that in your decision rule, your y is bigger than or equal to the threshold tau. And again, we have given such a conditional healthy. We are already given the conditional PDF of this random variable y. Okay, so when somebody is healthy, the PDF is given by such an exponential distribution with lambda h. So you basically compute, take integration from tau to infinity, and then you get this result. And we can see that in this example, if you reduce the decision threshold, then the misdetection rate will decrease, but the false alarm rate will increase. Right? So these two, you need to make a trade-off between these two types of errors, depending on how much you care about them. And then in the end, the overall probability of error is calculated as follows. So we are conditioning, this is a total probability rule, right? Where we decompose the entire, we partition the entire space by H0 and H1. So this is a total probability, where each of these two terms are computed here. And then if we know the prior probabilities, then we can calculate the total probability of error. So this is how we leverage the probability framework to develop such a binary hypothesis testing rules. Okay, so I think I will stop here, and you can start to work on homework 6, I think. And next time I will go over more examples on this. And also the solution to midterm 1 has been posted online. So if you are interested, take a look at the solution. And if you have any questions, talk to me in the office hours. So I will see you in the afternoon in the office hours.